Welcome to this e-lecture, which will be about multiple regression analysis. And first, what is the purpose with doing a multiple regression analysis? Well, we want to calculate a linear equation that describes the observed relationship between one dependent variable and a set of independent variables, x1, x2, x3, and so forth. And I want to establish the most complete explanation model possible. In this instance, for example, if we want to explain the variation in income, we include gender in our model, age, education, health, because we know that these independent variables have an effect on income and explains part of the variation in income. So we want to establish the most complete explanation model possible when explaining variation in the phenomenon we are interested in. The purpose is also can also be to examine the effect of a causal variable. And if you, for example, want to investigate how occupational status affect income, we have to control for spurious correlations by controlling for confounding independent variables prior in time, because occupational state, if we look at the effect of occupational status on income, we might part of this effect might be spurious, not the whole thing, but it might partially be spurious, because education comes prior in time and has an effect on both income and occupational status. So we have to include education in our model and control for education to really find whether there's the effect of occupational status controlled for education. And furthermore, if we are going to look at the effect of education on income, it might be that we overestimate the direct effect of income of educational income, because it partially goes through occupational status on income. So part of the effect of education goes through the mechanism. This mechanism goes from education through occupational status on income. So it's not a direct effect, so to speak. We use multiple regression analysis both to control for variables that are confounding because they come prior in time, but also for controlling for intermediate variables and for whether there is a mechanism, a potential mechanism. And how does the multiple regression equation, how does it look like? And it's really, we just really add more regression coefficients compared with the bivariate model. So A is still the constant. It's the expected value on the dependent variable when the independent variables equal 0. And then you have several regression coefficients, and that's how much the expected value on the dependent variable changes when one independent variable increases with one unit, value unit, and the other independent variables are kept constant. So if we want to look at the effect of this regression coefficient on y, the dependent variable, we have to hold these two ones constant, and we can just put in 0, for example, as the value, or another value, but we have to keep them constant, and then just let this regression coefficient, the value on this regression coefficient, vary to see what the effect of this regression coefficient on y is. Or we can keep this one constant and this one constant, and then let this second regression coefficient vary to see the effect on the dependent variable. And then we have the error term, or the residuals, which is the deviation between the predicted and observed values on the dependent variable. But let's take a look at an example. And as in the bivariate regression, this is what we cannot explain. This is our error term. This is a deviation between the predicted and the observed values on the dependent variable that we cannot explain in our model. But of course, we won't explain as much as possible. But there will always be an error term part which we cannot explain. Let's look at an example. is it possible that life expectancy is not only influenced by the general government expenditures on health as percentage of total expenditures on health, but also, or maybe rather, per capita total expenditures on health, whether it is private or government expenditures? And so in our example, we're going to use life expectancy as our dependent variable. We have general government expenditures on health as one independent variable, but we're also going to include a second dependent variable, which is per capita total expenditures. And let's look at a scatter plot where we have health expenditures per capita and life expectancy. And as you can see here, there's a curved linear relationship between these two. So the relationship is not linear. And when the relationship is not linear, we cannot include this in our model straightforward because we are running a linear regression model. So, and then we presume that all the independent variables we include are actually the relationship between the dependent variable and the dependent variable and the independent variable is linear. But in this example, the relationship between this independent variable and this dependent variable is not linear. So we choose to code the independent variable as a dummy variable, where countries in the lowest quartile is coded 1. Those countries that 25% of the countries that uses less on health per capita is coded 1, and the rest is coded 0. So the 75% that uses most is coded 0. So what results do we get? Well, first and foremost, we get a constant, which is 69.7 years. And that if both the government share and the per capita health expenditures are equal to 0, life expectancy is 69.7 years. But this is only a technical interpretation. It's not meaningful because there are no countries where the government's share of the health expenditures are 0. So it's only a technical interpretation. And then we have this coefficient, which is which shows that the average life expectancy decreases or increase by 0.06 years for each percentage point higher government share of health expenditure when we control for per capita health expenditures. So it's actually an increase. It's a positive coefficient, so there's an increase in life expectancy when for each percentage point higher the government's share of health expenditures. But it's significant. So this is lower than our levels of the p-value is lower than our levels of our significance level. So it's less than 5%. So we can be sure that this is actually different from 0. But countries that have low per capita health expenditures have on average 12.8 years lower life expectancy than the rest, the 75% rest that uses more on health than these 25% that uses the least. So they have this is a negative. We see that there is negative coefficient. So there's a decrease, or on average they have a 12.8 years lower life expectancy in these countries where they use the least on health per capita, when we control for the government's share of total health expenditures. And it's statistically significant. P-value is much less than our chosen level of significance, so we can be not only 95% sure, but 99.999, somewhere down here. It's a number, but we can be 99% sure that this is different from 0. And the model explains 46.6% of the variation in life expectancy, so it explains a lot of the variation in life expectancy. And what happened? Well, because the coefficient for government expenditures as health on health as percentage of total expenditures on health is significantly weaker, because if we had not included per capita health expenditures, the coefficient would be 0.2. So for each each percentage point increase in the government's expenditures on health, the life expectancy increased by 0.2 years, but now it's only 0.06 years for each percentage point the government's expenditure on health increases. There's only a increase in life expectancy of 0.06. So it's still statistically significant, but it has a higher p-value, and the model explains more of the variation in the dependent variable. And the explanation is really that the variable per capita health expenditures is positively correlated with both the dependent variable and the other independent variable. So per capita health expenditures is positively correlated with life expectancy and with the government's share of health expenditures. So if we don't control for this, we overestimate the effect of the government's share of health expenditure, the effect of that on life expectancy. So this bivariate relationship is partially spurious. So the positive relationship between life expectancy and government share of health expenditures exists because countries with a higher per capita health expenditures have both longer life expectancy and higher government share of health expenditures. So it's partially spurious. Another example: does health problems cause poor monthly salary? Well, this is the constant. So that this is the average monthly salary for those who do not have health problems. And in this example, we can actually interpret a constant in a meaningful way, because having no health problems, zero health problems, is actually a value or a substantial value on or a meaningful value on the independent variable. And the regression coefficients, it's a negative correlation for each additional health problem. Monthly salary is on average 549 kroner, Norwegian kroner lower. So, well, from this model it seems that actually health problem causes poor monthly salary. But is the correlation between health problems and poor monthly salary spurious? Well, if we include sex, where men is 1 and women are 1 and men are 0, well, then we can interpret the constant again. This is the average monthly salary for men, because men it has the value 0 on sex, who do not have health problems. So they earn on average 19,459 Norwegian kroner. Whereas the regression coefficient for health problems, for each additional health problem, monthly salary is on average 322 Norwegian kroner lower when gender is kept constant. So it's actually, this one went quite much down. It went from over 500 to 321, so it's much lower. And the regression coefficient for gender shows that women earn on average 6,270 Norwegian kroner less than men when they are equal in terms of health problems. So why is the effect of health problems reduced? Well, some of the relationship are nonsense, or it's really spurious due to the influence of the underlying or due to the variable gender, which is really, it comes beforehand in time. So women have a lower monthly salary, so it's really, there's a negative effect of sex on monthly salary, but they have also more health problems, which also so there's a positive correlation between sex and health problems, and there's also a negative effect of health problems on monthly salary. So it's kind of that's why we have to control for sex coming prior in time. So we really because this is partially spurious, the effect of health problems on monthly salary. So when we keep some of those who have many health problems and low salary have so because they are women. When we keep gender constant, compare people of the same sex, the effect of health problems is weaker. So yeah, this illustrates the importance of controlling for several variables as we do in multiple regression analysis. So that was the e-lecture on multiple regression analysis. Thank you so much.